So this is a very intuitive example. We have a curved flow. The flow rotates in front of your eyes, and we compute the rotationality. That's fine. But it might deceive you in the sense that you might think, well, any curved flow will have a vorticity. This is not correct. So let's see this example.
Excuse me, can I ask something about the equation? So in the first cross, you simply did the derivative first, and then you crossed the ER and E theta. But in the second, you put omega R on the front, and then you did it. Now, how come you treat these two terms differently?
Okay. This partial. Okay, ER is the direction, so just get it outside.
Okay.
ER will be crossed with whatever comes, okay?
Okay.
What comes? You have partial, this is differentiation of this term. This term is a magnitude and direction. They are multiplied together. So you're differentiating, so the output is two terms.
Oh.
Partial R for omega R times E theta, this is the first term. Partial R for omega R is omega, times E theta. Okay, so you have E theta, and remember we had ER cross on the beginning. Okay, waiting. So go next. The second term, still here, I'm not done here. What's the second term? Well, ER cross is waiting. Partial R now is acting on E theta, and I have omega R outside.
Okay.
Partial R acting on E theta as what? Partial R acting on E theta, actually this is 0. We don't have something like this, okay? So let's go here, the same thing. We have partial theta acting on this term. So acting on that guy first, and then acting on this guy. So partial theta acting here is 0. Let's go away. Then partial theta acting on E theta. So we have omega R outside. So here is the omega R outside, and here is 1 over R. And we have E theta cross what? Partial theta acting on E theta. Partial theta acting on E theta is negative ER. And you
okay.
So it's not, you need to do it carefully. It's not. Okay, so for this thing, you have here, this is a particle, this is a point in the fluid. We attach to it two elements, two lines, A and B. After a while, here is the point, here is this axis along the flow, okay? So this is the flow, and the flow goes omega R, the tangential velocity goes omega R, okay? So we started vertically, now we are rotating in this direction, okay? We have omega A here. What about this guy? Well, let's see what happened to these points. Which point, the right point or the left point that moves faster? Is it the right or the left? For this red thing, is it the right end or the left end that moves faster?
Right.
The velocity is omega R, so it's proportional with R. So the right one moves faster. So the right one will be here, and the left one will be there. And the line itself is also rotated in the same manner. Okay? So you add them together, you get what we had before. You will see in a minute why I'm doing this. Because the second example, the bathtub sink. So what we have is we have a sink. Okay? In the sink, the flow also seems curved, right? But rotates faster outside or inside. Is it faster towards the center of rotation or faster towards outside? It's not like a rigid body where it's omega R. No, it's very fast when it comes closer to the sink. So it's actually 1 over R. So the U is V theta. It's completely tangential. It's curved flow. But this guy is proportional to 1 over R, some constant over R. Okay? It's a curved flow. Do you think it has vorticity or not? Let's see. Let's compute the nabla cross u from here. So we again partial r, er plus 1 over r, partial theta, e theta, and partial z, ez. This is crossed with c over r, e theta. So let's do these terms again. Partial r of this guy, just bear with me for a minute if you want to do it. Partial r for this guy is negative c over r squared, right? And you left with er cross e theta. Here is er cross e theta, which is, we know this is ez. Plus partial r acting on e theta, this is 0. The second term, we have partial theta on the magnitude, this is 0. And then partial theta for the direction. And we have c over r outside. So c over r outside with r here, this is c over r squared. E theta cross partial theta e theta. So partial theta e theta, this is negative er. And this guy is ez. Okay? And you can see clearly this is negative c over r squared ez. This is c over r squared ez. The vorticity is 0. So how come the vorticity is 0 in a curved flow? Let's see. So the exact same picture, we're gonna draw it here. The two lines, this guy and that guy, okay? So this guy is along the fluid path. So when we come here, here is that guy. So it actually rotates, right? What about the red one? Which is faster? Is it the right or the left? Which point is faster? The right point or the left point? The left point, because it's faster towards the center. So when it comes here, the left point will be here and the right point will be there. So actually it rotates the other way around. It rotates in the negative direction. So it was straight like this, now it is. And the two angular velocities happen to be equal and they are opposite, of course, so they cancel each other. I will show you videos for these things in a minute. Let's consider the third example and I'll show you videos. Any questions so far? So what we get from this example is that curved flow does not necessarily imply vorticity. Right? You can have a curved flow without vorticity, irrotational curved flow. Okay? Any question about that? So the whole flow is curved, it's curved path, but the fluid particle itself doesn't rotate about itself. Okay? Any question? Okay, so we'll take the other extreme. Okay, what about the other way around? Does vorticity imply necessarily curved flow? Let's see. The third example is maybe boundary layer or velocity gradient. So we have over a wall here, we have flow with some u infinity. Okay? But at some section here, we know that the velocity here is how much? This is 0. And the velocity here is your u infinity. Okay? So in between, we have a velocity distribution. Okay? So let's see, for example, let's say that here inside this boundary layer, this is the velocity distribution, changes with y. The velocity distribution is only along the x-axis. The flow, if you look at it from away, the flow is just straight. There is no rotation, there is no global rotation, right? But the fluid particle itself may rotate while moving straight. Okay? So let's get that. Let's get any distribution, any function for u here. Seems to be y squared. Okay? If this is x and this is y, let's assume it to be y squared. Actually, the Poiseuille flow is something like y squared. So So y squared, and it's in the I direction. Okay? Let's apply our very basic definition for vorticity. So omega is partial xi, partial yj, and partial zk cross y squared I. Actually, nothing changed except the partial y. Nothing will give you anything except the partial y.